So we talked about spectral lines and we talked about fundamental subatomic particles relevant to chemistry. And so let's go into the spectral lines of one of those atoms, the simplest of the elements, simplest of the atoms, hydrogen. And you may remember from your general chemistry course something called the Bohr model, which looked at these spectral lines and came up with a kind of an empirical constant. It's called the Rydberg constant, this 1.097 times 10 to the 7th inverse meters value. And those are energy units. You can put it in a lot of different energy units, but that's one of them. And this model was, saying that, hey, it's kind of like the electrons are orbiting sort of like a sun, like planets around the sun. Electrons are orbiting the nucleus in that way. It turns out to be totally wrong, but it does explain hydrogen. It can't explain any higher order elements, as we'll talk about in a bit. But so you got these different spectral lines from these different quantized states and this constant. So this formula can allow you to predict at what wavelengths these spectral lines will show up. The spectral lines have different names depending upon where they are. The names aren't important for anything, but it's basically 1 over the wavelength, lambda equals r, that constant, that empirically derived constant, 1 over the the initial quantum number squared that you start at, this quantum state, minus 1 over the final quantum numbers squared. So let's do a practice problem with this, right? And so in order to do that, I'm going to need to know the formula, the Rydberg formula. Okay, so that's R1 over N1 squared minus 1 over N2 squared. And what is the problem asking me for? What is the wavelength of light emitted when an electron transitions from n equals 4 to n equals 1? Okay, so that tells me n equals 1. That's my initial is 4, and n equals 2, and 2 equals 1, right? And so 1 over lambda is going to be equal to r. R, of course, has a value on the previous slide. R has a value of 1.097 times 10 to the 7th. And then 7 times 10 to the 7th inverse meters times 1 over n1 squared, so that's 4 squared, so it's 1 over 16, minus 1 over 1 squared is 1. So it's 1/16 minus 1. If you do all that, that comes out to 1 over lambda is going to be equal to negative negative 102,84375. Okay, so we take the inverse of that to solve for lambda. 1 over that ends up being, let's see, I have it here, 9.7. Okay, so two significant figures I'm doing here. 9.7 times 10 to the minus 8 meters. This was meters inverse. These are dimensionless, right? These are dimensionless, so we just have meters inverse. Then we divide it by meters here, so that gets meters. And that is equal to, if we times by 10 to the 9th, convert to nanometers, that'll be equal to 97 nanometers. So that's going to be an ultraviolet line that we're talking about. Why is it negative? So I drop the negative sign there. Why is it negative? Well, it's emitting light. So this is just a sign convention thing. I mean, you could write this formula flipped. These parts of the forms, you could switch the definitions to N1 and N2, wouldn't matter much. But it's a sign convention thing, right? So the negative is supposed to be saying, hey, I'm emitting light. The light's going away from the atom. If you, and that makes sense, right? You're at a high state, n equals 4, n equals 1, an electron dropped down, so it's going to be more stable at n equals 1, and in the process, it's going to, emit an h nu of a photon packet. The opposite would be if you went from n equals 4 to n equals 1 to n equals 4, right? Now you're going up, so light is going to have to come in to excite that electron up into the higher Bohr orbit, the higher energy level. Okay, so there's just an example of this hydrogen line, spectral line problem. We'll be solving a lot of problems together in these lecture videos.